Designing flexible sensors in KiCad. In this tutorial, you'll learn how to design a custom 30-button touchpad for Trill Flex for printing on flexible PCB. We'll walk you through all the steps in KiCad from start to finish. The final design that we'll come up with will look something like this. What's a Flex PCB? Flex PCB has been in common usage since the 1950s, but this manufacturing technique has recently become readily available for hobbyists and makers. Instead of the hard FR4 material that common circuit boards are made of, which is a type of fiberglass, Flex PCBs are printed on a malleable polymer substrate called captan. Trill Flex is the latest addition to the Trill family of capacitive touch sensors. Trill Flex easily conforms to curves, bends, corners and more, giving you the freedom to create projects with touch surfaces that are virtually any shape. There are two parts to Trill Flex. The base, where you'll find the Trill chip and a high-density connector, and the flexible sensor, made from Flex PCB that attaches to the base via a clip. As the sensor is detachable, you can swap out the default sensor for one of your own designs. There are many different possibilities you can choose from when designing your Trill Flex sensor, because Trill offers 30 channels of capacitive sensing that can be arranged in any way. Each channel can act as a single sensor, or can be combined in interesting ways, for example to make sliders or other types of interfaces. A note about Flex PCB manufacturing. Although they've gotten far more affordable recently, Flex PCBs can still be quite pricey in small quantities. Setup. Download and install KiCad. This tutorial uses KiCad 5.1. KiCad is an open source program for PCB design and one of the best tools you can learn for creating your own circuit boards. It's available for free for Windows, Linux and Mac OS on the KiCad downloads page. It's really worth investing some time to get to know KiCad. There are lots of tutorials available online and especially on YouTube. This tutorial should be a good introduction to some of the tools in KiCad and the basic principles, though bear in mind that as we're designing a sensor, we won't actually be placing any components on our PCB. Rather, it will just be capacitive pads that we're drawing. Download the KiCad Trill Flex libraries. The folder contains a single file for the symbol library, trillflex.lib, and a folder for the footprint library, trillflex.pretty. The symbol represents the electrical connections of our flex sensor and is needed for the schematic part of our KiCad project. The schematic is where we define all the components that will be included in our circuit and describe the electrical connections between them. The footprint library, trillflex.pretty, contains different footprints for the Trill Flex connector. These footprints represent the part that will be added to your PCB, including the symbol library. So let's open up KiCad. Now the first thing we want to do is load in the Trill Flex symbols and footprints. To include the symbol library, we want to go to Tools at the top of the screen here and go to Edit Schematic Symbols, or we can click directly on this button here. Once this is loaded up, we want to go to Preferences and Manage Symbol Libraries, and then look at the global libraries. This brings up a dialog box. Click on the small folder icon on the bottom left of the box. This is going to open up a File Explorer window, and here we just want to navigate to the files that we downloaded. Mine are in my KiCad Libraries folder, Added Symbols. Find this trill.flex.lib and click Open. And then we'll see this has added an additional line here at the bottom. So that's the symbols now fully loaded. We can click OK and close the symbol editor, including the footprint library. So we return to the main KiCad window. So now we want to navigate to Tools and Edit PCB Footprints. Or again, you can use this button here. And so once that window opens up, you want to go to Preferences, Manage Footprint Libraries, and go through a similar process. So we click on the folder. Now we want to find the trillflex.pretty folder, which I put here in my added footprints. There we go. And we want to click OK. Click OK once more, and now we're all ready to go. Set up a new KiCad project. So the next thing we want to do is to set up a new project in KiCad. To do this, go to File, New, Project, and give your project a name. This creates a project with 2 files in it by default. Add the Trill Flex symbol to the schematic. So let's open up our schematic by double clicking on it here. Next we want to select Place, Symbol, and click anywhere within the schematic to place our symbol. This is going to load up the library, and we can now select the Trill Flex symbol. If we scroll down to the bottom here, Trill Flex connector, and press OK to add this to our schematic. You have to click one more time to actually lay the symbol down. There we go. That's all we need to do for now. We can save this schematic and close it. Add the Trill Flex footprint to the PCB. So now we want to open up the PCB side of our project. So we can do that by either double clicking on this file here or clicking this button here. This brings up this black screen, which is where we're going to be designing the sensor. The first thing we need to do is go to Tools and Update PCB from Schematic. This brings up a dialog box asking if you would like to annotate the schematic. Click Annotate, which will open the PCB window again, and then click Update PCB. And once this is done, you can click Close. You'll see that we now have the footprint underneath our cursor, and we can just click to place that footprint anywhere on this black screen. And we can just zoom in to have a better look at that. Getting familiar with the footprint. We've taken care of the hard part of the sensor design for you, which is this pigtail lead. It has a 0.5mm pitch and is basically an FFC 32 channel connector. The Trill Flex footprint has 32 individual wires and 2 sides to it. One side, the top side here, is the part which will make contact with the connector on the Trill Flex baseboard. The other side is where we're going to make our connections to each of these 32 channels. It can be easier to work with the footprint when it is oriented in another direction, and you can rotate the footprint by dragging a box around it to select the whole object and then clicking R. You can also click and drag to move the footprint around the screen. We suggest orienting the connector side of the footprint to the left and drawing connections on the right. Looking at the default Trill Flex design. The Trill Flex footprint has 32 connections. The outer 2 connections are both ground and can be used to connect to a ground plane. We'll look at this later. On the sensor that comes with Trill Flex, you can see the ground is connected to a horizontal strip before the slider begins. The remaining 30 channels are our capacitive sensing channels. On the included Trill Flex sensor, these are connected to each of the zigzag-shaped pads. If you want to see how these pads are designed, you can download the KiCad files for the Flex Bar PCB here. Drawing the pads. In this tutorial, we'll break each of these 30 channels out to 30 touchpads to make an MPC-style button interface. As a general rule of thumb in this PCB, we want to draw our pads on the bottom layer and draw our connections on the top layer. So the first thing we want to do is to switch to the bottom layer of the PCB, which is called B.Cu, as in bottom copper. You'll see currently we're on F.Cu, the top layer. So let's switch onto B.Cu from this list at the top. You can also do it here at the side. Next we want to click the Add Filled Zone button on the right of the window. That's this one here. If you hover over any of these buttons, you'll see the tooltip appear. This mode lets us draw shapes on the PCB by clicking to place corner points. Let's click on the screen where we want to start drawing and the settings window will appear, but we can just ignore that for now. All we want to do is confirm that we're drawing on the bottom layer, which you can see here. Click OK, and you'll now see we have a line coming from that first point that we placed. So I'm just going to place some points here, and then I can double click to finish the shape. Now you see I've done a pretty bad job here of drawing a square. So I tell you what I'm going to do is I'm going to delete this and I'm going to change the grid size to something more appropriate for what I'm wanting to draw. So what I want is a 10mm square with 2.5 millimeters in between each of the squares that I'm going to draw. So I want to change the grid size to 2.5 millimeters here. And this will make drawing much, much easier. So again, let's add filled zone. And now I'm just going to start drawing. Again, make sure I'm on the bottom copper layer. Okay. So now we know that if we just do 4 clicks down, and then 1, 2, 3, 4 across, we will get nice square. And then I can draw another here. Again, click OK. Down. We can now duplicate these squares by switching to select mode, selecting them and using Ctrl D. Note that our design is actually upside down in comparison with how it's going to be eventually used. This is why we're drawing our pads on the bottom copper layer. As a final step, we want to round the edges of the squares. Double click on a square, and this is going to bring up that settings window we saw before. Find corner smoothing on the bottom left and select fillet, and we want to apply a 2mm fillet to each of these squares. Now if we click OK, we can see that that's happened to that one square. That's great. We like the look of that, we like the size of the fillet. So now if we click on that square again and go to export settings to other zones and click OK, that will apply it to all of the squares that we've already drawn. Adding a ground plane. I'm going to add an additional polygon to this design, which is going to be connected to the 2 ground channels. So again, I want to go to Add Filled Zone, and I'm going to do this on the lead at a potential bend point. This is to add a bit of strength to the lead and to shield the connections that are on the other side. Later in this video, I'll show you another design with an alternative ground plane layout. Now actually I'm going to switch back down to our more fine-grained grid, just so I can shape this a bit. I want it to chamfer in here and here. And then, you know what, I think I'm going to move the whole thing in a bit. Okay, that looks good. Connect the nets. A net represents an electrical connection between 2 elements in your design. In this step, we're going to create a net between each of the points on the connector and each of the squares. We're going to number the pads from top left to top right according to this diagram. Now if we zoom in on the connector itself, we'll actually see that it mentions these nets here. At the top, we have net C1 pad 32 going all the way down to net C1 pad 1. Now remember that net 1 and net 32 are both of our ground connections, and so it's actually 30 channels that are in between these two that we're going to use for the capacitive pads. To connect a pad to a net, you just need to double click on it and then select the relevant net in the settings window. So this one we want to connect to pad 31. Select that and press OK. There's now an electrical connection between these two. Double click on this one, we want to set this to 30. And so on until all the pads are connected. Make the connections. Now we're going to draw connections from the various pads that we have on the connector footprint here to each of the square pads that we have drawn. Before doing so, make sure that the Trill Flex connector is in the right position for your design. We can route electrical connections between the Flex connector footprint and the squares using the Route Tracks tool on the right hand side, which looks like a green line here. We want to route on the top copper layer, so make sure you're on f.cu on the layer selector at the top. To begin routing, click on the pad of the connector. We're going to start on pad 31 here, because let's remember that 32 at the top is going to be connected to our ground plane. So let's click. You can then draw out the path of the trace by clicking to place bend points. And you can see here that the pad that we want to connect to is highlighted. Our traces are on the top layer of the PCB, but we need to make a connection to the pad we drew on the bottom layer. To do this, we place a via, or a hole through the PCB that allows us to route traces from one side to the other. To place a via while routing, type V. Click to place the via. You will now be on the other side of the PCB and you'll see the colour of the trace that follows around your cursor has changed from red to green. We now need to make one more connection from the via that we've placed to the pad itself, which is as simple as just clicking. Let's look at the next pad. Some conventions to be aware of while drawing your traces are that you should avoid right angles. There are many different styles of routing PCBs and everyone does it a little bit differently. You can either choose to follow the diagrams we have here or you can define your own paths. Draw an outline. We now need to define the overall shape of the sensor. This outline has to include the connector as well as all our pads. On the Edge Cuts layer, we're going to use a combination of the Add Graphic Lines tool for straight edges and the Add Graphic Circles tool for rounded corners to build up the whole outline of our sensor. You can now define the outer shape of your design by clicking and adding in points. We've opted to leave about 0.5 mm where possible between the sensor pad and the outline. Run the design rules and electrical check. The design rule check, or DRC, confirms that everything is connected correctly. To run it, click on the ladybird icon at the top menu bar. If there are any issues with your design, for example unconnected traces, then this will show up as a red arrow on the PCB to highlight where the problem is. Once the DRC is passed, you should be ready to send your files for manufacture. Let's have a look at another design for Trill Flex. In this design, instead of having the 30 channels used as individual buttons, they are used in groups of 10 to create free sliders. Here we've used a zigzag pattern similar to that features on the Trill bar to allow interpolation between each of the pads. The ground plane in this case acts as a divider between the free sensors. Generating the file for manufacturing. There are now several companies who offer Flex PCB manufacturing, but in this video we're going to show you how to place your order at OSH Park. OSH Park are dedicated to open source hardware and have a large library of designs on their website that you can browse and print with them. You can also find out the exact specifications of the Flex PCBs that they can print. On the front page of oshpark.com, you can just drag and drop your PCB file. On the next page you'll see a nice preview of the board as it will be printed. If you see the warning about your project not containing a bottom solder mask, don't worry about this unless you're expecting to see something there in your design. This warning is just telling us that there is no exposed copper on the bottom layer, which is expected in this design. On the next page, you can get a detailed preview of every layer that is included in your design. On the next page, select Flex PCB from the options available, and you're now ready to place your order. Getting your sensor ready to use. There's one last step before you can start using your new sensor. Before connecting your sensor to the Trill Flex board, it's necessary to add a small piece of tape to the connector to make sure it fits snugly into the board's clip, otherwise it can move around. Take a look at the sensor that came with Trill Flex and you'll see a small piece of stiffener plastic. A layer of sellotape or 2 layers of Kapton tape works a treat. Now you're ready to test your sensors out. Plug it into the Flex connector board, run Flex settings as a start. So that's it for today. Thank you for following this tutorial and I hope it's been useful.